Hello and welcome to today's video. In today's video, we're going to be going over topic 3.4, the chain rule. So to start out, I have some review questions, and it's always good to review what you've already learned, just reinforces what you know. So for this first problem that we have the derivative with respect to time of cosine of t plus sine of t. Well, the derivative of cosine of t is negative sine of t. The derivative of sine of t is cosine of t. So we get negative sine of t plus cosine of t is our answer. Next, we have a exponent, the derivative of e to the w plus w to the power 4.392. Very random number there. So the derivative with respect to w of e to the power of w, that is just e to the w, and then the derivative of w to the power 4.392 well, that is just going to be 4.392 w to the power of 3.392. Alright, and how do we do this last one? We can't. We don't have a way of differentiating a function and a function yet. Well, in today's video, that's what we're going to do. We're going to build the tools so we can eventually solve this derivative. So this problem has given us the chain rule. And the chain rule goes, if g is differentiable at x and f is differentiable at g of x, then the composite function f, capital F, is equal to f of g of x, is differentiable at x, and f prime is given by f prime of x is the derivative of the outside of the inside times by the derivative of the inside. Alright. And if you want to see that in Leibniz notation, it goes dy dx is equal to the derivative of f with respect to u times by the derivative of u with respect to x. Alright, so what does this really look like? Well, I have three examples. The first one was our first problem that we solved. So we take the derivative of the outside function. So really the outside function here is x to the power of 1/2. So let's say that we have 1 over 1/2, and then we are going to have, or rather, let's rewrite this first. So it's d over dx of x squared plus 4 to the 1/2 power. Well, you're going to start by taking the derivative of the outside function. Well, the derivative of the outside function, in this case, is just going to be like x to the power of 1/2 is going to be 1 over 1/2 square root of x squared plus 4. Times by, now you have to take the derivative of the inside function. The derivative of x squared plus 2, that's just 2x. This 2 and this 2 will cancel. So we're just left with x over the square root of x squared plus 4. And that's our answer. Alright, the next one, we have a composite function dealing with trig, so scary, very scary. So the derivative, so we want to know the derivative of sine of cosine of x times by tangent of x. So this is a product rule and a chain rule. So we start out by taking the derivative of the first function. The derivative of the first, well, we have to do a chain rule. So the derivative of sine is cosine, and its argument still remains the same of cosine of x, times by the derivative of the inside. The derivative of cosine is negative sine, times by tangent. Alright. Plus, well, this first part will stay the same, so it's just the first sine of cosine of x times by the derivative of tangent. The derivative of tangent is secant squared of x. And now just expanding this all out, we will get negative cosine of x times by sine of x times by tangent of x plus sine of cosine of x times by secant of x, or secant squared of x. And that's our answer. And for this last one, you can either treat this as a quotient rule or a chain rule. Me personally, I believe it's easier to do it as a chain rule. So d over dx, and this is really just x squared plus 1 to the negative 1 power. So we use the power rule first. So it's going to be negative x squared plus 1. Subtract 1 from the power, so it becomes negative 2, times by the derivative of the inside function with respect to x, which is 2x. So we would get an answer of like negative 2x over x squared plus 1 squared. And that's our answer. So now we're going to look at the derivative of the general exponential function. So you may recall that I've stated in the past that the derivative of b to the power of x is equal to the natural log of b to the power of x. But why is that? Well, let me show you why. Well, let's see. Let's say that we have e to the x. E to the x is the function where its derivative is always proportional to itself. So the derivative of e to the x is e to the x. Well, we can rewrite any exponential to be an e to the x. So what we do in order to do that is we say that it will be e to the ln, the natural logarithm of b, to the power of b times by x. And you can confirm that this is the same thing because you can rewrite this as e to the ln of b raised to the x power if my pencil wants to work. And as thus we can show that this inside here, the e and the ln of e, or sorry, the ln and the e will cancel, leaving us with b to the power of x. As thus showing that b to the power of x and this are equivalent expressions. Alright. So, what do we want to do with this? Well, we will take the derivative of this e to the natural log of b raised to the power of x. Well, I want to kind of bring this x inside of here. There we go. So whenever we take the derivative of this is a chain rule derivative. While the derivative of e to the ln of bx, that is still just e to the ln of bx. But now we have to take the derivative of this inside function. Well, the derivative of this constant, which is the natural log of b, times by the derivative of x, which is just 1. So we are finally left with e to the ln of b times by x times by ln of b. This e and the ln cancel, so we are left with b to the power of x times by ln of b, showing that this above statement is true. Ln of b times by bx. There we go. Apparently I just forgot to write another b up there. Alright, so now I have two functions for us to take the derivative of. One of them is a bit easier than the other. So for this left one, this is the same thing as saying, like, we're taking the derivative of e to the x. So let's actually write this out. We're taking the derivative of e to the negative theta with respect to negative theta times by the derivative, of negative theta with respect to theta. So writing it out like this, we see that this over here, the left side is just e to the negative theta, once again. The derivative of negative theta with respect to theta, while the derivative of negative x with respect to x is just negative 1. So what we get is this expression is equal to negative e to the negative theta. Alright. Now that we got that done, let's work on this beast. Well, this is a product rule and an exponential. And a chain rule. So we start out, we take the derivative of the first. So we get 1/2 square root of x times by pi to the x squared over 2. Alright. Plus the square root of x times by the derivative of pi. So we still have so the derivative of pi in this case is going to be the natural logarithm of pi times by pi to the x squared over 2 times by the derivative of this inside function. So that's going to be 2x over 2. So we are just going to be left with pi x squared over 2 over 2 square roots of x plus the natural log of pi square root of x times by actually we're going to call this an entire x to the power of 3/2. And then, just to make this a bit cleaner, we will have pi x squared over 2. And that's our final answer. Alright, now time for the hard part of this video, which is proving the chain rule. So, we're going to start out, we're going to say that we're going to define a change in y. So y is equal to f. So y is equal to f of x. That's our first starting point. And that is going to change that this change in y is going to be defined as f of a plus change in x minus, or f of a. Okay. So if we want to know, like, the derivative of that, we are going to divide both sides by a change in x. Then we are going to take the limit as this change in x approaches 0. And this is equal to f prime of a. So, we are now going to denote a new number, which name is going to be epsilon. Alright. And the limit as change in x goes to 0 for this epsilon is actually going to be the limit as the change in x approaches 0 of the change in y over the change in x minus f prime of a and this is going to give us, because this change in y over change in x, this is going to quite literally just be f prime of a minus f prime of a. So this goes to 0. Okay. However, using this, we now, we are going to say that epsilon is equal to our change in y over our change in x minus f prime of a, which after multiplying through by change in x, we are going to get change in y is going to be equal to f prime of a times by the change in x plus an epsilon change in x. Okay, now what do we do? Well, this is where the fun begins. Now we are going to define, or now I'm going to actually prove it. Suppose u is equal to g of x. And is what's it called? Differentiable at x is equal to a, or at a, to shorten that up. And y is equal to f of u. Alright. Is differentiable at g of a. Alright. If change in x is an increment an x and change in u and change in y are corresponding increments and u and y then we can use equation 6, or we can use our equation which we are going to say that our equation up here is this guy. Yeah, this guy. So we are going to get change in u is equal to g prime of a times by a change in x plus an epsilon, and we'll call it 1, change in x is equal to and this really can just become g prime of a minus plus an epsilon plus epsilon 1 change in x. Okay, now what do we do? So then, our change in y next, we're going to say that as change in y is equal to our f prime of b, which is really this f prime of a. This g and the f are going to be the same. Alright. Or the b is, sorry. This value right here is our b. Okay, so what do we do now? Well, that's f prime of b times by a change in u. As our u is now, it's changing, is equal or plus our epsilon 2 change in u. And that's just the same thing as f prime of b plus epsilon 2 times by the change in u. Alright, now what? Now if we substitute the expression for change in u from equation 7, which is really just this equation right here, we will get change in y is equal to f prime of b plus our epsilon 2 times by our g prime of a plus our epsilon 1, alright, times by a change in x. Now what do we want? If we want the derivative, we need to divide both sides by a change in x. So we get a new change in y over change in x is equal to f prime of b plus an epsilon 2 times by a g prime of a plus an epsilon 1. Alright. And then as some of our previous equations show us, as change in x goes to 0, change in u will go to 0. So taking the limit as the change in x, because we want dy dx, we're going to take the limit of everything over here as that goes to 0, as change in x goes to 0. Goes to 0 of change in y over change in x, which is the limit as change in x goes to 0 of f prime of b plus epsilon 2 times by g prime of a plus epsilon 1. Alright. And as that limit goes to 0, this b, the epsilons, because as we showed way earlier, is as the change in x goes to 0 of these epsilons, they go to 0. So we're really just given this f prime of b times by this g prime of a. What is f prime of b, you may ask? Well, fb, as we've already stated, is g of a. So we get f prime of g of a is equal to, or sorry, not is equal to, but times by g prime of a. And that's our final answer. Well, I hope y'all found this video informative. I hope y'all are enjoying this chain of proofs that I've been doing. I hope y'all have a wonderful rest of your day, and I hope y'all enjoyed. Goodbye.